Hey guys, so I apologize to everyone who tuned in to Zoom today for our quiz review. My internet is scheduled to be out for the next 4 hours, but I still want to go through this quiz review with you guys so you can be ready for that quiz. And like I said on the Google Classroom, I will extend the quiz window. It is available now. It'll be available Friday, Saturday, Sunday, Monday until 11:59, and then Monday we can schedule a Zoom session and go over any questions you guys have, because I still want you to have that opportunity to ask questions before you take your quiz if need be. All right, so question 1. A student added a 1 centimeter strip of magnesium ribbon to 30 milliliters of hydrochloric acid. 4 trials were performed under different conditions, and then here are the results. Which 2 trials should be used to test the effect of surface area on reaction rate? So the key for this problem is that we only change one variable at a time. Let's say you were to change the temperature and the concentration, and the reaction went faster. We wouldn't know if the reaction went faster because of the temperature change or if it went faster because of the concentration change. So whenever we are designing an experiment, it's really important that we only want to change one variable at a time. So our best option to test surface area would be trial 1 and trial 4. So trial 1 has a large piece of magnesium ribbon. Trial 4 has a bunch of small pieces of magnesium ribbon. They're at the same temperature and they're at the same concentration. The key for size, you're still using a 1 centimeter strip. The only difference is if you have a large strip, pretend that was 1 centimeter, you have very little surface area available for collisions. And the more collisions we have, the faster that reaction is going to go. So if we were to take that 1 centimeter strip of magnesium ribbon and we were to cut it up into a bunch of little pieces, well, now you're exposing a lot more surface area. The more surface area you have exposed, the more collisions you can have. The more collisions you have, the faster the reaction's going to go. But again, the key is only change one variable at a time. If we want to test surface area, the only variable that should change should be the surface area. Temperature should stay the same. Concentration should stay the same. Number 2. Same data, but we want to know which trial is going to produce the fastest reaction. So this should be easy to remember because they're all direct relationships. If we want to increase the rate of reaction, we should increase the surface area. We should increase the temperature. And we should increase the concentration. So trial 1 and 2 are out because they have they have a small surface area. A large piece of ribbon has a small area exposed. We also want to increase temperature. So the trials at 50 degrees would be faster than the trials at 25 degrees. And then lastly, we want to increase concentration. If I used a 2 molar solution instead of a 1 molar solution, that would be my fastest. So trial 3. It has an increased surface area by using small pieces of magnesium ribbon, an increased temperature of 50 degrees Celsius, and an increased concentration. Number 3. So we have this reaction, A produces B, and we want to calculate the rate of disappearance of A between 10 and 20 minutes. So I want to look at A at 20 and A at 10. All right, so to calculate rate, we are going to take the change in concentration and we are going to divide it by the change in time. It is also important to note rate is always positive. So anytime we have rate of disappearance, we want to add a negative sign before our calculation. Or you could always just keep bigger number minus a smaller number, that way rate is always going to be positive. But traditionally when we do like the change in, we normally do final minus initial. Alright, so the rate of A at 20 minutes is 0.42 molar. Its concentration at 10 minutes is 0.51 molar. And then I'm going to do the change in time, 20.0 minutes minus 10.0 minutes. And we should get 0.0090 molar per minute. Pay attention to your units. So sometimes time will be in seconds. This time it's giving you time in minutes. So my units would be molar per minute. Alright, another example for rate. Now we're going to do the rate of appearance of B between 20 and 40 minutes. So again, rate is going to be the change in concentration divided by the change in time. I like doing final minus initial. So at 40 minutes, concentration of B is 0.34 molar minus its rate at 20 minutes, its concentration at 20 minutes, 0.23 molar, all over change in time. Final minus initial, 40 minutes minus 20 minutes. And for this one, we should get 0.0055 molar per minute. All right, number 5, calculate the equilibrium constant, which is just KEQ. And then we're going to predict whether reactants or products will be favored. Alright, so first, whenever we are doing KEQ, remember that we always exclude pure solids and pure liquids. Also, when we are doing KEQ, we are going to take the concentration of the products and we are going to divide by the concentration of the reactants. So KEQ is products over reactants. Well, I don't have any products because I crossed out my only product because it was a pure liquid. So we're just going to put 1 there. Reactants are going to go in the denominator. And remember, if you have more than one reactant or if we had more than one product, we would multiply them together. Alright, so now we just need to plug in our quantities and solve. So these are given to us in the problem. And we should get KEQ is equal to 5.21. Next, we need to predict if the products will be favored or the reactants. The This one would be the products, and the reason that we know the products are favored is because KEQ is greater than 1. So remember, for our KEQ expression, it's products over reactants. So if you have more products, your answer is going to be greater than 1. If your numerator is bigger than the denominator, your answer is going to be greater than 1. All right, number 6. So same type of problem, just another example. Again, the first thing that you want to look at is your states of matter. We always exclude solids and liquids. So first thing we want to do is write our KEQ expression. KEQ is equal to products over reactants, each raised to the power equal to their coefficient. So hydrogen chloride gas has a coefficient of 2, so we're going to square it. If you have more than one product or more than one reactant, we multiply those values together. We don't add them. All right, products over reactants. Next step is just to plug in our values. All right, and then lastly, we need to solve, and I believe we should get about 5.6. Last step is to make a prediction. KEQ is greater than 1. That means this reaction favors the products. At equilibrium, the products are going to be greater than the reactants. All right, number 7, Le Chatelier's principle. Given this equation, determine which way equilibrium will shift. So for pressure, I always like to think of pressure in terms of volume. They're inversely related. If we increase pressure, pressure is increased, volume is decreased. That's important to know. And next, we want to count the total number of moles of gas on each side of the arrow. And we're going to do that by looking at our coefficients. In this case, they're all going to be 1. So on my reactant side, the left side of the arrow, I have 2 moles of gas. On the right side of the arrow, I only have 1 mole of gas. So if I increase pressure, I decrease volume, that means I have less space. It's going to shift to the side with less moles of gas. Think if you were in a small space. You would want to be trapped in that small space with less people because you have less room. If we increase pressure, we decrease volume, we have less space, it shifts to the side with less moles of gas. All right. Temperature is decreased. Anytime you add a substance, equilibrium shifts away from that substance. They both start with A. If we subtract or remove a substance, equilibrium stays on that side. So let's say I were to remove heat. Well, heat is on the right side. I'm subtracting heat. Equilibrium is going to stay on that side. Equilibrium is going to shift to the right. Le Chatelier's principle says, if we stress a reaction, it is going to shift to reduce that stress. So if we decrease temperature, we remove that stress by producing more heat. So equilibrium has to shift to the side that heat is on. C. Concentration of C2H4 is increased. That means I'm adding it. If I add it, it shifts away. C2H4 is on the left. If I add it, it's going to shift away. It's going to shift to the right. D. Concentration of hydrogen is decreased. If you subtract a substance, equilibrium stays on that side. Hydrogen is on the left. If I subtract hydrogen, equilibrium is going to shift to the left. Again, it's all about getting rid of that stress. If I decrease the concentration of hydrogen, I restore equilibrium by producing hydrogen. Equilibrium has to shift to the side that hydrogen is being produced on. And then last one, E, concentration of C2H6 is decreased. Again, if you subtract a substance, equilibrium stays on that side. C2H6 is on the right, equilibrium would shift right. Number 8. So first, I have a delta H value that is negative. That means this reaction is exothermic, which means heat is being produced. So we can think of heat like a product. Hopefully we can identify this as a combustion reaction. I have my combustible material plus oxygen producing carbon dioxide, water, and it's releasing heat. All right, we want to list as many ways as possible to increase the amount of carbon dioxide produced. So it's not saying that we're adding more carbon dioxide, it's saying we want to produce more carbon dioxide. So I want to produce more carbon dioxide, and carbon dioxide is on the right side of the arrow. That means that we must force equilibrium to shift to the right. If we force equilibrium to go to the right, we're going to produce more carbon dioxide. All right, so anytime we add, it shifts away. So that means to force equilibrium to shift to the right, we could increase the concentration of methane. We could increase the concentration of oxygen. Since they're both on the left, if we increase, it's going to shift away, it's going to go to the right. Well, we could also subtract anything on the right, because if we subtract something on the right, it's going to stay on the right. So I can decrease the concentration of H2O, or I could remove heat. I can decrease the temperature. Pressure is not an option because I have 2 moles of gas on the left and I have 2 moles of gas on the right. So if we were to increase the pressure, decrease the volume, we have less space, it's going to shift to the side with less moles of gas. Well, I have an equal number of moles of gas on each side of the arrow. So pressure is not an option. All right, last 2 problems are going to be rice tables. And again, the key for a rice table is you're given an initial concentration rather than an equilibrium concentration. So R is for reaction. And again, sometimes you won't see this. Sometimes you'll see an ice table where they don't have this reaction row, but I like it just to, help me keep things straight. All right, I is for initial concentration. H2SO4 has an initial concentration of 0.032. Before the reaction begins, I don't have any products. So their concentration is 0. Reactants will always decrease in concentration. Products are always going to increase in concentration. We don't know how much they're going to increase or decrease by, so I'm going to put an X there. The other thing that we need to be careful for in this step is to look for coefficients. If any of these had a coefficient other than 1, we would want to bring that coefficient down. 0 plus x is x, 0 plus x is x. Next, it tells me that H2SO4 ends with a concentration of 0.024 molar when it reaches equilibrium. So I know at equilibrium, the concentration of sulfuric acid is equal to 0.024 molar. I also know at equilibrium, H2SO4 is equal to 0.032 minus X. So I can set those two quantities equal to each other and solve for X. All right, once we solve for X, we can now solve for our remaining concentrations. In this case, both concentrations of the products are going to be equal to X, so their concentration is 0.008 molar. All right. So I solved for the concentration of sulfur trioxide, solved for the concentration of water. Last thing is we need to solve for our equilibrium constant. So again, it's always going to be products over reactants, each raised to the power equal to their coefficient. And then make sure you're plugging in your equilibrium concentrations. And we should get 0.0027. All right, last problem for the review. Carbon monoxide has an initial concentration. So again, anytime we have an initial concentration, that is your key that we're going to need a rice table. All right, carbon monoxide has an initial concentration of 0.35. Water has an initial concentration of 0.40. We always assume, unless we're told otherwise, that the initial concentration of the products is 0. Reactants always decrease in concentration, so minus X. Products increase in concentration plus X. And again, everything has a coefficient of 1, so that's why it's minus 1x or plus 1x. So at equilibrium, the concentration of carbon monoxide will be equal to 0.35 minus x. Water will be equal to 0.40 minus x. Again, just combining these two. Carbon dioxide will be equal to x. Hydrogen will be equal to x. Last piece of information, we are given the concentration of carbon monoxide at equilibrium. So I know at equilibrium, concentration of carbon monoxide is equal to 0.15. Well, I also know at equilibrium, concentration of carbon monoxide is equal to 0.35 minus x. So I can set this equal to 0.35 minus x, and x is going to be equal to 0.20. All right, now I can solve for the remaining concentrations. H2O is going to be equal to 0.40 minus x, and x is going to be 0.20. So the concentration of water is 0.20 molar. And then lastly, both carbon dioxide and hydrogen are equal to x. X is 0.20, so both of their concentrations are 0.20 molar. Last step is to solve for our equilibrium constant. Products over reactants. And now I just need to plug in all of my equilibrium concentrations. So the concentration of carbon dioxide and hydrogen are both 0.20 molar. The concentration of carbon monoxide at equilibrium was given to us, that's 0.15 molar. And then we solved for the equilibrium concentration of water. It was 0.20 molar, which should give you a final answer of 1.3.